All right, hey everyone, and welcome to this talk on custom data structures in managed Postgres using WebAssembly. My name's Andreas. I'm a senior principal engineer at Workday, where I work on the Pecan employee voice product, or just Pecan for short. So this talk is based on personal experience trying to scale an application using managed Postgres. So about 5 years ago, Pecan was shifting from targeting customers of a couple of thousand employees to targeting customers with hundreds of thousands of employees, really some of the biggest companies in the world. And this turned out to be quite a challenge. The core operations in our application couldn't really manage to keep up with these 100x increase in data volumes. And this talk describes how we managed to solve that problem, how it applies more broadly, and how you might use it to solve problems with the stuff that you tackle. I don't think Pecan's story is unique. So many teams and companies choose a relational database as the foundation of their products or services because of its versatility, right? Postgres is great at very many things. It can solve many problems really well. But over time, as your needs evolve, gets more complex, maybe it's scale, maybe it's something else, you turn to extracting part of your workload to more specialized databases. That's not a decision you should take lightly, though. There's a lot of operational overhead in adopting new database technology. You need to understand how to debug it in the middle of the night, being on call, monitor it, back it up, disaster recovery. What do you have, right? It's definitely like something that you shouldn't take lightly. And this is where Postgres extensions can be like a pragmatic solution. You get some of the benefits of a more specialized database while staying within kind of the comfy realm of what you know. Maybe it's Postgres, maybe something else. Unfortunately, this is where another trend can kind of work counter to that, which is managed services. Using managed Postgres is great for your ops team, right? They get to focus on core business need and not have to worry on some of these more mundane tasks that your cloud provider can probably solve better than your ops team can. Unfortunately, running extensions in Postgres requires native code, right? That's part of an extension. And cloud providers don't like that. They don't like just running any people's C code as part of the service that they provide to you. So all the major cloud providers, they have these lists of, okay, you can install these extensions, but not those. And whether it's Google Cloud Platform, Azure, or AWS, it's pretty limiting. Like they have a very specific set and they don't easily add to this set. And coming back to the story of Pecan, we had a very specific wish. We wanted this particular extension called PG Rowing Bitmap, and it was just not on the list. So we were kind of like, okay, how do we solve this? What do we do? Well, an obvious solution is, well, why not ask them, right? They offer this kind of, hey, send me an email, fill out this form, what have you, and we'll take a look. So we wrote this carefully crafted love letter to AWS in our instance, but it just seemed like they piped it to dev null. I never heard back, and if you look at kind of more broadly, you will see these Google Cloud Platform forums where people have asked, hey, can you add this, can you add that? And people just never hear back. And even now, 5 years later, my Google Cloud Platform request is just no answers, except for more people saying, hey, I also want this. So why are cloud providers being so conservative in their approach here? Well, the basic premise of the cloud is we're all sharing some infrastructure. That's kind of how they can provide their service to us. And while we might be like a nice innocent tenant running RDS on this server here, other tenants might not be so nice. So if they allowed us to install just any extension, there could be bugs, right? There could be security vulnerabilities, and the email tenant might actually impact your workload So it is kind of to the benefit of everyone that there are these allow lists and that they are being careful on our behalf. So as much as I've been extremely frustrated with these allow lists, they do actually make sense. So the problem here is really kind of how can we install an extension running untrusted native code while still doing it in a safe way on a managed service. If only there was a way to kind of run untrusted code in a safe way. Well, this is the logo of V8. It's the JavaScript engine running under the hood in the Chrome browser. You probably use it, maybe, every day, visiting websites, running code from people you have no relationship to, no kind of trusted relationship to. You don't know what they're doing with their code. And still, it turns out pretty well. Like, we're not seeing problems every day with that. And even more importantly, this the V8 engine can run WebAssembly, which is a way that to run like near C code in an efficient manner. And more interestingly, there's an extension, Postgres extension called PL-V8 that actually allows you to embed the V8 engine inside of Postgres. And this extension is supported by all the major cloud providers. It's on the allow list of both GCP, Azure, and AWS. So that kind of back in the day sparked the idea, hey, can we use PL-V8 to run these unapproved extensions as in our managed Postgres instance? And I wish the answer could be yes, you can run any extension taking this approach, but unfortunately not so. Many extensions require kind of integrating with Postgres APIs, only available via C and or some kind of native code, and that's just not something we can achieve via PL-V8. But what we can solve is an interesting subset of extensions that define custom data types. And that's going to be kind of the focus of this session. How can we replicate the behavior of an extension providing a custom data type using PL-V8 and WebAssembly? And it's split in 3 parts. First, we'll look a little bit more at PL-V8. What is it? How do you use it? How do you run WebAssembly in PL-V8? Secondly, we'll review what is a custom data type? How do you define it? Both kind of stock Postgres using C, but then also contrasting it to this approach. And lastly, we'll look at a concrete use case where we apply this and see some real nice benefits. So first up is PL-V8. As mentioned, this takes the PL-V8, the V8 engine and embeds inside of Postgres. So you can imagine for every Postgres connection, you actually have a V8 instance and that you can kind of use for running JavaScript and WebAssembly. And we'll look at what that looks like in practice. And the first step is basically just, hey, let's create the extension. That's kind of step 1. And this allows us then to define a function in JavaScript rather than some of the other supported programming languages. You can see here at the end, we have language PL-V8. And even though the code you see between the double quotes could look like almost any language, this is actually JavaScript that adds up 2 numbers together and returns back an int. So extremely simple function, and just kind of to prove that this is how you would use it, we can actually call this function and it can accurately add 2 numbers together. So success. Getting started with kind of writing user-defined functions with PL-V8 and JavaScript is really simple. WebAssembly, less so. It's a 3-step process that I'll take you through. First up, you need some WebAssembly, right? And in our case here, we're going to have some C code that will compile to JavaScript and WebAssembly. Secondly, we'll figure out how to kind of make sure that V8 is initialized, having this available. And thirdly, we'll actually define a user-defined function in Postgres using kind of this WebAssembly function. So before we had a simple function for adding up two numbers, and here we've written the same function in C. It looks very similar because, syntax is similar, but this is kind of the C version of adding the numbers A and B together. To convert it to JavaScript and WebAssembly, we'll use a tool called Scripten. I'm not going to go into too much detail, and there's like a ton of flags that you can configure when compiling C to WebAssembly, but the basic premise is you run it on your C code, you get out this add.js file in this case, and if you look at the contents of this file, it basically defines a JavaScript object called module, and it will have properties that correspond to the functions from your C file, except prefixed with an underscore. So here, previously we had our C file with the add function, and it's going to be available under module._add here. So that was step one. Step two, we want to initialize the V8 engine with all these functions available. So we'll take all the output from that file we just made with mscripten, and we'll put it into this plv8 init function, and we'll take all the properties of the module and set it on this. This is just like a small hack such that we'll have all these functions that we defined in the C file available in scope when we make user-defined functions later. And then we'll set a special property called, or a special configuration variable called plv8 startproc to the name of this function. So every time v8 is initialized, it's going to run this function, it's going to evaluate the JavaScript in the WebAssembly, and make our functions available in this scope. That was step two, which means we're now ready to actually use this in a user-defined function. So before we had add_js that adds up two numbers. Now we have add_wasm that adds up two numbers. And it basically just invokes the C function we had previously. It's here, you can see it's called _add. And if we try to use it in an example, lo and behold, it can also add up two numbers correctly. So this was like a whirlwind tour of how to use plv8, how to compile C code into WASM and use it from a user-defined function in Postgres. And that's kind of one of the building blocks we'll use in a little bit. But for now, we'll turn to how to define custom data types and what those are. So you might be familiar with data types in Postgres like text or int or array of int or whatever it may be. But Postgres is actually really extensible, and you can define your own data types that do something else. And by default, this is something that happens via C. To make it concrete, we'll look at this particular extension and kind of try to look a bit under the covers, pgrowing bitmap. Well, what is it? What is pgrowing bitmap, or what does it do? Well, it defines a user-defined custom data type called rowing bitmap, which is a really effective way of representing unsigned 32-bit integers. So you can imagine a set of the integers 1, 2, 3. That can be a rowing bitmap, and it's going to represent that using very few bytes, and it's very efficient for doing set operations on top of that. So the union of two bitmaps, the intersection of two bitmaps, the cardinality, so the size of the intersection of two bitmaps, so on and so forth. All the operations that you might know from set theory, and it makes it available in Postgres as a data type. If we kind of look at such an extension as an example of defining a custom data type in Postgres, there are kind of a couple of layers. The first layer is the core library. So that's the rowing bitmap library, which is totally independent from Postgres and which is also used in a ton of other open source databases. The second layer is what I've called here the Postgres adapter. That's kind of taking the C library and then applying it in the context of Postgres. So using kind of the Postgres APIs, Postgres data types. The third layer is then in SQL, defining the custom data type and the functions on top of that. So it's basically kind of the user-defined functions. And we'll kind of skip looking at the core library and the Postgres adapter. Those are kind of pretty complex C code, but we'll kind of take a peek at what does this last layer look like, because we'll try to replicate those layers in just a bit. So when you need to define a new custom data type in Postgres, kind of the core bit is basically telling Postgres, how do you serialize it? So kind of how do you get a blob of bytes from the specific data type so it can store it on disk or have it in memory somewhere? And how do you deserialize it? Given it's stored on disk somewhere, how do you kind of hydrate it, you could say, to kind of your data type? And I'll talk briefly about how does this look like for PG-ROING bitmaps. So first you have to do kind of this weird shell type definition, which is almost like a forward definition, and you can think of it as that. We've just said there is going to be some data type called ROING bitmap, and I'll tell you in a bit, Postgres, how to kind of interact with it. So firstly, we have to define this deserialization function that we'll define here. It says, hey, I'm going to take an argument of type C string, which is the blob of bytes, and I'm going to return you a ROING bitmap type. The actual definition, it's in the Postgres adapter. It's in C code. So please find it there, Postgres. And similarly, we'll define a serialization function that says, given I have a ROING bitmap of some type, I can convert it to a blob of bytes, here what's called the C string. So please call the C function in the Postgres adapter, which is written in C. And given those two functions, we can now define the actual data type, saying, okay, now there's a new data type, it's called ROING bitmap. Here's how to serialize it, here's how to deserialize it. And at that point, Postgres you can start using it in tables and user-defined functions everywhere you would use int, text, so on and so forth. But we can't actually do anything useful with the data type just yet, right? We don't have any interesting operations on top of it. So that's kind of what we'll turn to next. And we'll look at two functions that are kind of going to be a thread throughout the presentation. And the first one is, we want to be able to create a bitmap, and in this case, from an integer array. So given an argument of type int array, we're going to return a bitmap. And when you do that in a native extension, you just say, hey, the implementation is over in CLAN in the Postgres adapter. Please go call that when invoking this function. And similarly, we'll have a function called RB and cardinality, so computing the size of the intersection of two bitmaps, which will take two bitmaps as arguments and return an int. And again, the function is implemented in C. So using that in a concrete example, let's imagine we have a table. It's called native bitmaps, has a simple primary key and a column called bitmap of type ROING bitmap. We can insert two rows into this table with IDs 1 and 2, and it's going to be representing the integer sets 1, 2, 3, and 2, 3, 4. And now we can compute the size of the intersection of these two bitmaps, calling the RB and cardinality function, and it's going to return the value 2 because they share the integers 2 and 3. So this was a whirlwind tour of how the PG-ROING bitmap extension works. And the question is now, how can we get the same functionality using PLV8 without relying on C code? You saw there were tons of user-defined functions we had to write that all relied on C code. What can we do instead? So when we want to replicate it, what we'll do is the core library will represent in WASM. We'll basically take the ROING library, compile it to WASM, and that's going to be the core library kind of layer in our custom data type when taking this approach with PLV8. The Postgres adapter that was previously in C will write in JavaScript instead. And then lastly, we'll hook everything together using SQL just as if it was a regular native extension. The last point here is that where before we could rely on Postgres transparently calling our serialization and deserialization function when interacting with the bitmaps, we now have to do it ourselves. So the data type for Postgres will be byte A, which is basically a blob of bytes. It doesn't know anything about it, doesn't know it's actually a bitmap. So now we'll try to write RB build and RB and cardinality with this in mind. And to do that, we need to understand like what functions are actually available in the rowing library that we compiled to WASM. So we'll look at the rowing header file and we'll find 3 functions we need. The first one is rowing bitmap of pointer. So given a pointer to an array of unsigned 32-bit integers, it's going to create a bitmap. The second is called rowing bitmap portable size, which given a bitmap tells you what's going to be the size of this bitmap if serialized. And the last one is called rowing bitmap serialized, which given a pointer to a bitmap and a pointer to a buffer, will write that into the buffer. So these are all 3 library functions that will be available to us via WebAssembly. And when compiled with Emscripten, they will be available under the prefix, these names, but prefixed with underscore. So we'll try to implement RB build WASM such that it behaves in the same way as the native function using these functions. There are a few details I have to gloss over just to kind of keep scope here. And when interacting with WebAssembly, it kind of has its own heap, its own memory, and there's a bit of magic about kind of copying things in and out of that heap that I'll gloss over. We'll begin with copying this array of integers into the WASM heap. At this point, we can call our library function rowing bitmap of pointer on kind of this elements pointer, and that's going to return to us a bitmap. Then we'll ask, if I serialize this bitmap to bytes, what's going to be the size? And then similar to if we were kind of in C land, we are going to malloc a buffer of that size. This is allocating memory in the WASM heap. And at this point, we can serialize the bitmap into that buffer. And lastly, we'll kind of copy that out of the WASM heap and be able to return it to PLV8. So this function behaves pretty much like the RB build function that you just saw previously from the native extension, except we can run it purely using PLV8. The second function that we want to try to replicate is the RB and cardinality function. And we'll go back and look at the header again for how to implement this. We'll first need to use the rowing bitmap deserialize function that tells us if you have a blob of bytes, how do we deserialize it into a rowing bitmap? And secondly, we'll use the library function rowing bitmap and cardinality, which given 2 pointers to rowing bitmaps computes the intersection, the size of the intersection. So with those 2 in mind, these are going to be available as WASM functions under the same names, prefixed with underscore. So let's try to implement RB and cardinality WASM. It's going to accept 2 parameters of type byte A. Those are the bitmaps we want to compute the intersection of. It's going to be in their serialized form because Postgres doesn't kind of do it for us. It doesn't know it's a custom data type, and it's going to return an int. Again, we'll kind of prefix this with a bit of magic, copying the data into the WASM heap. And then we'll call our deserialization function to get the actual bitmaps. And lastly, we can call the rowing bitmap and cardinality function to compute the size of the intersection. And previously, you saw kind of how we used that in a particular example. And just to kind of demonstrate that this works exactly the same. We can create a table called WASM bitmaps with a simple primary key and a column called bitmap of type byte A. This is kind of the key difference. Previously, the type of bitmap was rank bitmap. Now it's type byte A because rank bitmap Postgres doesn't actually know that this is a special data type. It's just a blob of bytes to Postgres. And we can insert into this table, just as before, 2 rows, IDs 1 and 2, representing the sets 1, 2, 3, and 2, 3, 4. And we can compute the cardinality of the intersection of these two bitmaps exactly as previously. So you see that kind of our queries look almost as if it's a native data type. Like there's not really much telling you that it's not a native data type, but Postgres doesn't really know. So now we can we've shown how to replicate the functionality of the pgrowing bitmap library without any native untrusted code in sight, just using PLv8 and WASM. And at this point, you might be wondering, okay, I've gone all through all these hoops. What's the payoff? And that's what we're going to talk about next. The example I'll give is kind of what I've coined faceted counting. Maybe when you go to your favorite shopping website or you're on LinkedIn or somewhere similar with kind of advanced search, you search for something, and then on the left-hand side of the screen, there's kind of these different properties of the items in the search result, and that allows you to kind of filter them down. Maybe it's the color of the product or when it was produced, who is the manufacturer, so on and so forth. And we'll do that in just kind of the context of documents. So we'll kind of have this extremely simple example, table documents. It has a primary key, and it has a facet IDs column, which is an array of IDs that kind of try to capture this. So facet ID 1 might mean published in 2020, and facet ID 2 might mean front cover of the book is green, or whatever it might be. So it's like a uniform way to describe different properties of the documents. And what we want to compute extremely quickly is the count of how many documents match 2 facets. So putting kind of this query into words, it's counting how many documents both have the facet ID 1 and the facet ID 2. That could be like the documents that are more than 10 pages and published in 2020. And that's actually not a easy problem to solve in Postgres if you have very many documents. The approach I'm familiar with, that's kind of the most, the fastest at this, is using a GIN index. GIN indexes are kind of part of stock Postgres. It's an inverted index. So it's going to keep track of, under the hood, what are the document IDs matching facet ID 1, what are the documents matching facet ID 2, so on and so forth. If you want to learn more about GIN indexes, there's a ton more material online. So I'll kind of just pause here in terms of going to depth with GIN indexes and just say, I'm not aware of any faster way of solving this with kind of just stock Postgres. If you plot the time to run this query by the number of documents in your table, here we have between 1 and 10 million documents. You'll see that it's from around half a second to a second, which is not like atrocious. But on the other hand, if you want to do many of these queries to serve a single interactive request, then it's going to be really slow, right? You don't want your user waiting for seconds while you're trying to load kind of this sidebar. Can we do better? The way to kind of solve this problem, at least for us, was to think about this as in kind of set theoretical terms. What we're trying to do is we have kind of all the documents matching facet ID 1. We have all the documents matching facet ID 2. And what we're trying to achieve is really to count how many documents are in the intersection, right? And what we can do is to basically represent these sets more explicitly in our database. What we'll do is we'll create a table called facet bitmaps with a facet ID as the primary key and a bitmap column, which contains all the documents that match that particular facet. Here I've kind of tried to show that the bitmap, the kind of underlying series value of the bitmap, we're basically storing this big blob of bytes that is really kind of this integer set under the hood. A way to think about kind of this facet bitmaps table is we could use a materialized view. That would be like a simple way of achieving a table like this, in it where we take all the documents, we group them by facet ID, unless the facet ID is array, and then we build a bitmap over the aggregation of the document IDs. That would basically achieve the table that you just saw. Assuming we had a table or a view like this, we can rephrase the query you saw previously about the count as an API and cardinality. Basically, you find the bitmap representing facet ID 1, the bitmap representing facet ID 2, and you count the intersection. If you graph the time to run this query against the original approach, this is what it looks like. So it might look like it's instant or 0. It's not really, it's just, the x-axis. But suffice to say that both pgrowing bitmap and the WASM approach is hundreds of times faster than using a GIN index for this particular use case. If we zoom in a little bit, this is what it actually looks like. So you'll see pgrowing bitmap using C is still faster, like approximately 3 times faster than using WASM, which is to be expected, right? Where WebAssembly is not as fast as native code, and we're copying data in and out of the WASM heap and whatnot. There's an overhead, right? But still, this is the difference between being like 500 times faster and being 150 times faster. And this is like a latency that's fast enough. You could do multiple of these and still have like a quite responsive interactive application. So what's the catch? One thing we've kind of not touched upon is maintenance and consistency. I showed you how to construct the facet bitmaps table as a materialized view, and you could choose to do that, right? And then every so often refresh materialized view. It's not going to be particularly efficient. And if you want to be efficient about it, you'll have to probably write custom application code to maintain this. Every time you touch the documents table, you have to go and update the facet bitmaps table, which is not that fun. And if you want to maintain consistency guarantees, so you want the facet bitmaps to always be perfectly in sync with the documents table, you'll probably have to rely on triggers or something. So making changes to the documents table in a transaction and updating the facet bitmaps table at the same time. So there are definitely kind of some overhead here and some gotchas that you'll have to think about when applying this pattern. Something else that we didn't kind of go into detail with is that manual memory management. So you did kind of see this odd alloc somewhere, and maybe some of you thought, "Hey, are you freeing the memory again?" And I didn't. So that's something you'll have to take into consideration as well. When you interact with the WASM memory heap, then you need to free stuff again, and it's not trivial if you're used to JavaScript. The last thing is called toast, and I don't know if you're familiar with it, but it's kind of the mechanism that Postgres uses under the hood to store rows that are big. Big typically means more than 2 kilobytes in size. So if you have a bitmap, which is say 1 megabyte, then Postgres will, under the hood, actually partition it into multiple rows and tuck it off in a separate toast table. And by and large, this is very transparent to you as a programmer, which is great. But then sometimes you get hit by these odd gotchas where interacting with toasted values is just a little bit different than interacting with regular values. So it's like a there be dragons thing here. And you want to look at your query plans to ensure that you're not inadvertently doing something stupid. Okay, so I'll try to just do a brief summary of all the material that I covered today. First up, you saw how to write functions in JavaScript and WebAssembly, compile it, run it inside Postgres using PLV8. We got to have our cake and eat it too, in the sense that we could write a custom data type and run it on managed Postgres. And if that's kind of a constraint for your business, that's great. I think it allows you to suddenly have new opportunities that you didn't have previously. And ultimately, this all boils down to you can solve some use cases much better. For us, this was like the difference between being able to scale to some of the largest companies in the world. And that's just something that was not achievable within the realms of Postgres otherwise. And we would have resorted to extracting this workload to a specialized database and taking the hit of that approach. Instead, we were able to kind of stay within the confines of Postgres. And that was a big win for us. I hope the next time you face a challenge scaling Postgres, feeling constrained by the extensions allowed by your cloud provider, that you'll think of this approach and maybe it can help you solve the problem. And with that, I just want to say thank you so much for watching, and yeah, appreciate it.